Everyone. My name is Simon Sponberg. I co-organized the neuroseminar series here with Bilal. And today we have a special treat. Professor Grace Leslie is a relatively new professor here at Georgia Tech. She's been here for a little more than 2 years now. She's in the School of Music, but her training is very interdisciplinary, crossing from performance music to cognitive sciences. She got her PhD at UCSD, where she worked at the Schwartz Center. And she's done just a whole bunch of amazing things since then. She's worked at a research at the ICRAM in Paris, which is this scientific institute for the study of avant-garde electronic music. She's a performing flutist, and she calls herself an electronic dance improviser, which is very cool. And she looks at the integration of how she can integrate brain-computer interfaces both into her performance and into her research in neuroscience. She's worked at the at the Newcomb Institute for Interdisciplinary Computation at Dartmouth, where she worked with people at the Media Lab at MIT, and she was been studying how you can combine and enhance the expression of music through BCIs. So it's going to be a great opportunity to hear about the diversity of neuroscience and its interface here at Georgia Tech. So Dr. Leslie, please take over for us.
Thank you so much, Simon. This is definitely a special treat for me. As a music technology professor, I tend to live in the world of applications of neuroscience concepts to seeing how we can apply the little that we know about the mechanisms behind how some of these theories work into things like music creation and understanding a little bit more about music perception. This is a real treat for me to branch out to all of you and see if we can get some conversation started about understanding a little bit more about what is happening in these projects that I'm going to be describing to you today. So the title of my talk today is Inner Rhythms, Music Technologies Informed by the Brain and the Body. I'm visiting you from the Brain Music Lab at Georgia Tech, which is housed in the Couch building in the School of Music, where we have a EEG lab set up, a 64-channel ActiChamp set up with a recording sound booth. And then we use that technology and also consumer-grade EEG, heart rate monitors, breathing monitors to send live physiology signals to software that we can then use to analyze how people respond to music that they're listening to, or take those signals and turn them into music so that the people can hear the changes going on in their physiology. So we also investigate biofeedback software that we can create using music. So I took the title of my talk from this quote by Edgar Varèse, who was one of our forefathers in the field of experimental music. And he wrote, "I dream of instruments obedient to my thought and which, with their contribution of a whole new world of unsuspected sounds, will lend themselves to the exigencies of my inner rhythm." So back then, that meant for Varèse that he was developing new kinds of technology to incorporate new kinds of sounds into the orchestral compositions that he was creating at the time. But I would like to think that if Varèse was working with this creative concept today, knowing what we do about brain signals, how we can record them in real time and turn them into sound, I would think that he would be thinking about work that is similar to what we're working on in our lab. So this is almost 100 years later. We're taking this concept and trying to reveal what's happening with these inner rhythms by converting brain and body signals into sound. in this, field of research that I'm going to be describing you today, I'm working with all of the different phases of this feedback loop that you see here, where we're developing methods to stream physiology data in real time to custom software. And that software is tasked with finding ways to classify and describe what is going on in that participant's body in terms of their cognitive state and their affective state at that time. And then we take those classifications that we develop and we find ways to control algorithmic music and video software based on those measurements that we're taking. And then we can actually use the way that we map these classifications to this audio and video to try to influence that participant's cognitive and affective state. So there's this whole feedback loop, and what I'm going to be describing you today is a number of projects, each of which encompass one or two or even three parts of this loop. And all along the way, you'll see that there's this common theme where we're looking at the shared mathematical properties that exist between these signals that we're measuring from the brain and the body, and the audio signals that the participant is perceiving in time. So you can see an example here. On the left, we have a spectrogram of Alvin Berg's violin concerto, where we're looking at what the frequency content is in time. And then on the right here, we have the EEG readout from a participant who is opening and closing their eyes in time. And since I'm a teacher, I will ask the crowd, can we think of a couple of ways that we're sharing some or seeing some shared physical properties in these two signals? And you can write that in the chat window if you're too shy to call it out. And it's okay to think creatively here. Anyone? I'm going to call on some of the names that I recognize. Okay, so Garrett's asking me, can I ask that again? I'm showing these two spectrograms here. On the left, we have a spectrogram of the music that somebody is listening to, and then on the right here, we have a spectrogram of a participant, unrelated participant who is opening and closing their eyes in time. But I would like to ask you if you see any similarities in this data, something in the signal properties that we see here in these spectrograms. So Joy asks, is the participant blinking in time to the beats? So this is actually not right. Okay, so Christopher says rhythm. So yes, you can see here that there is a kind of we can actually extract from this spectrogram here what the tempo is of this violin concerto by looking at how many seconds elapse in between these high amplitude vertical stripes that we see. And we can see the rhythm in the octave register too. So this is what Mr. Wu has said. So yes, we can actually look, and in addition to this, vertical temporal information that we can extract from both of these spectrograms, we can also extract spectral information by looking at these horizontal stripes as well. And so we can see not only what the relationship is between these events that are happening in time along the x-axis, but we can also look at what the relationship is between the various frequency components that we can see in our signal here. And we can see actually that there are a number of harmonics that we can see of our fundamental frequency, which are these kind of evenly spaced stripes in the left spectrogram example that we can see there. But we can also see harmonics in our EEG signal on the right there. So even though when somebody opens and closes our eyes, we can register that in the large amplitude shifts that we're seeing in the alpha range there. In this case, that's around centered around 11 hertz. We can actually see an indication of that in the 22 hertz range as well. So we're actually seeing a integer multiple of our fundamental frequency that is occurring there. So, this is just an extremely simple example that I wanted to show, what the really fundamental underlying assumption is that we are kind of taking to a creative extreme in all of these works that I'm going to be showing to you, which is that we can start to really creatively think about interchanging these sonic signals that we have over time and these inner rhythms that we can extract from our brain and body signals that we're recording as well. So as a first example here, I want to describe some of the first work that I did as a graduate student, which would really encompass this first part of this feedback loop, where we are setting up a controlled experiment, playing musical samples to participants, and then trying to judge to see what we can extract about their affective and cognitive state from that experiment. And so in this experiment, what we did is we played musical samples to our participants, and we asked them to move their hands expressively to the music in a very simple conducting motion. And you'll see in this animation what this looked like. We actually connected a motion capture system to our participants' hands and played back this real-time animation for them on a large TV screen in front of them. And we gave them this task of imagining that they have a friend in the next room who cannot hear the music that they're listening to, but they're really longing to know what this music is making them feel inside. And what we found was that we were able to, just by tracking just this single point light animation of our participants' movements, a internet audience who saw these animations afterwards were actually able to correctly classify what emotion was in the music sample that the participant was trying to express. And they were also able to determine if the participant was actually fully engaged in the music that they were listening to, or if they were distracted with a dual task, which in this case was performing a difficult math problem in their head at the same time. And when we compared the two different sets of expressive movement performances here, those where the participants were fully engaged in the music and very attentive as to what their friend was actually experiencing from their expressive movements. When we compared those trials to the ones where they were performing the dual task, we saw a difference in this independent component that was elicited at the beginning of each one of these expressive movement cycles. And this came through as a burst of alpha synchronization here in this temporal parietal junction area on the right side of the brain. And very similar research has shown that this area of the brain becomes particularly active during tasks that require theory of mind, or basically placing your mind into the mind of someone else. So we saw an indication here that this synchronization of movements leading to this expressive movement was actually integrating motor planning with this theory of mind idea. So we're actually showing that this idea of expressing some kind of inner emotion through this cyclical movement was actually tied to the motor planning of that movement itself. At the same time that I was performing this work, trying to see how we can describe and classify internal affective state during this music engagement, I was also tasking myself with figuring out how we might be able to take those judgments that we make of people who are listening to music and what they're experiencing internally, and how we can translate that into creating new music. So at the time, my colleague Tim Mullen and I found a way to create a model in the lab of high focus or high engagement in musical listening, and actually use that to control a algorithmic composition engine. At the time, all we had available to us was a single channel NeuroSky headset. So this is actually showing age at this point. The original instantiation of this project we ended in 2010. But we can see here an example. This is a very classic example of taking a classic BCI approach where we're trying to classify what is going on for a user and what their intent is, and basically translating that into some kind of feedback so that over time they can learn how to control a cursor on the screen or the way that a musical composition is created. So you can also see in the example that I showed you before, the performance example that I played for you at the beginning of this talk was an example of actually taking a very similar software as this, and then using this exact same EEG calculation to control music plugins on a very complicated synthesizer program. And what I actually found was that this kind of approach where I go on stage as a performer, and then I make these kind of classifications of what I am experiencing cognitively or affectively on stage, and then translating that into music, actually became a very limiting thing to do. I found that I would end up building a model of my experience in the lab so that I could control using alpha biofeedback my level of focus, and then be able to create changes in a musical composition on stage. Did not give me a lot of expressive bandwidth to work with when I was on stage. I ended up finding out that as a musician, it was a lot more satisfying to kind of bypass this computation stage where we're working with trying to classify cognitive state, and rather to work with algorithms that take raw data, perform some necessary filtering to get rid of muscle artifacts and other kinds of time series information that we don't want to hear in our signal, but then find ways to more or less convert that raw time series data directly into music. And with that algorithm, I basically started a new kind of music performance practice where I go up on stage and instead of using a brain-computer interface system where I have trained myself to be able to control certain indices in the software, I now have developed ways to control lower level EEG features and have that information that comes through in that spectral information, in that time information, translate more directly into that sound signal. And so I'll play a example of what that sounds like for you now. I can describe to you a little bit about what's going on musically in this sample here. You can see, even as compared to the previous music, brain music performance that I showed you at the beginning of this talk, there's relatively little movement here. There's a limitation to how much muscle artifact I can take out of my signal in real time, and so that's forced me to learn how to perform without moving very much. Or to move in a very specific way that I know is not going to interfere with my EEG signal as much. And you can also hear that as far as music goes, this is very relaxing, calming music. And what I found is that the kind of limitations that are placed on me as a performer in needing to have the kind of control, the ability to influence the EEG data that I'm sending to the software actually forces me to play music that sounds much slower, much more contemplative. All of these events are kind of spread out in time to provide me the space to be able to have this kind of control over that signal. And so as a performer, this ended up being a much more satisfying system to work with. I knew that I had come up with something that was very musically unique because it actually made the music sound a very particular way in response to how this algorithm had been engineered. Okay. This is a shameless plug for my music website where you can stream all of this music for free if you would like to hear this. So this is Grace Sounds at Bandcamp. So I'm going to shift themes a little bit here because for me, the most satisfying part of this work is trying to think ahead into the future and see the kinds of engineering that I've been able to do in service of the creative impulses that I have as a musician, seeing how those actually might be useful in a clinical setting in the future. I had the chance to work with a few epileptologists and neurologists at Dartmouth Hitchcock Hospital when I was a fellow up there to see in one case how I might be able to take this exact algorithm that I developed as a performer and to see how we might be able to apply this for the diagnosis of different seizure types. This is the algorithm in a simplified nutshell here, where we're basically taking the spectrum of the incoming EEG signal. We're taking the spectrum of incoming sound or sound that is stored on a computer hard drive. And then we're taking those two spectra and multiplying them or convolving them in the time domain. And then what we end up getting is this combined EEG sound, which almost sounds like we're kind of smashing together the spectrum and time frequency information that we have from this EEG, and we're kind of imprinting this onto some kind of sound. In the case of my performance work, I use vocal and flute sounds that I'm recording in real time, but we can use any kind of sound for this. And in the case, with the work that I did in the hospital, we also applied some spatial filtering so that we actually looked at what the 1020 location was for every EEG signal that we recorded from a patient's EEG when they were undergoing monitoring in the hospital. We applied spatial filtering to that so that when you heard the resulting sound on a pair of headphones, you would actually hear that channel of the EEG coming from a similar location as what the channel was on the participant's head. So if the EEG was recorded from FCZ, then you would hear that sound coming from the center of your head in the front. So we actually found that when we played these resulting sounds to people with seizure identification training and people without, that we actually had a surprising level of efficacy in how they were able to identify seizure activity from background activity in the EEG, but also they were able to classify different subtypes of seizures. So I would find that, I think that this could be a useful clinical tool in cases where sometimes in hospitals they are paying people with seizure classification training to look at a video EEG readout over time if a patient is being monitored. And the one thing that the auditory system is very good at identifying is when time series data starts to change from some kind of background rhythm. And so in a lot of ways, being able to identify the seizure activity through the ear might actually be a more efficient way to do this than by looking at a visual readout. So this is just a kind of technique that I have proposed to the epilepsy community that, perhaps in the future, this might be a useful thing to use. I'm also going to talk today about a few projects that involve the other side of this feedback loop that you see here. So how can we take the kinds of assumptions that we have about music, knowing the way that the auditory system works, and how can we engineer new kinds of music to invite particular kinds of physiological signals in the brain or in the body? So during the same fellowship as I mentioned to you before, I was working with Dr. Barbara Jobst, who is one of the inventors of the NeuroPace electrical stimulator that is designed to be implanted in the brain and detect seizure activity in a epilepsy patient and then produce a kind of flat square wave at 50 hertz of electrical stimulation into the brain to interrupt that seizure activity. And then, so as a music composer and an electronic music composer, when I learned about how this technology works, I thought, this is very similar to, the way that I work with square waves and sound. And I knew that we create these kind of auditory evoked potentials as listeners in the brain when we hear musical sounds. So I thought, even, mostly as a creative idea, it would be neat to see what happens in the brain when we produce these kinds of regular auditory pulses and to see if we can actually create beneficial stimulation. Now, of course, at the same time, I had been a postdoc at the MIT Media Lab where Annabelle Singer, our colleague, was a postdoc working with Li Hui Sai. They had figured out that you can create a train of visual stimulation at a gamma band frequency, and that can actually create beneficial changes in Alzheimer's pathology in mice. So I was actually working in the affective computing lab a few doors down from them when I heard about this research, and I instantly thought, we have to find some ways to see if this can work in sound as well. So when I moved up to Dartmouth, we then started these experiments where I was engineering musical sounds, and I can play for you an example of what one of these sounds like. So this is an example of a musical tone that is engineered to have, a fundamental tone that's at that 40 hertz gamma frequency, and then I'm basically modulating over time what the strength is in the harmonics of that 40 hertz tone. So this was actually one of the more pleasant stimuli that we used in our first experiments. But we published last year our results where we were able to first show that this entrainment is actually happening in the brain. So this is an example of what we're seeing in our intracranial data here, where we see a 40 hertz spike in response to these 40 hertz engineered tones. But more interestingly, Robert Kwan, who's a PhD, MD PhD student there, applied one of the template matching filters that they've developed in the lab to be able to count how many intracranial, IEDs or interictal epileptiform discharges that we see in the patient's intracranial data while they're being stimulated with these sounds versus the baseline periods when they're not. And we found that for the patients who tended to exhibit very high numbers of these spikes in their data, this stimulation actually reduced those spikes. So it showed that there was an effect of this stimulation on one of these markers of epileptiform activity in the brain. What we're doing right now is trying to investigate different forms of stimulation. We're trying to, figure out what the best kind of signal is to use, and if other frequencies besides gamma have a greater or lesser effect for the patients. During my time at the Media Lab, I was really interested in seeing how we might be able to affect somebody's breathing, and in particular, if somebody needs to attend to that signal very strongly or not. So we actually ran this experiment where I produced music that displays or kind of imparts the feeling of a really idealized breathing envelope. We had figured out from previous research that if somebody breathes 6 breaths per minute, that actually creates the most ideal restful state. And so I produced music that breathes at 6 breaths per minute, and it sounds something like this. And we actually piped this music into our experiment chamber while subjects were doing a really boring reaction time task. And we told them that the music was in there, simply to provide, a little bit of stimulation for them because the task was going to be so boring. And we recorded breathing, we recorded galvanic skin response, we recorded EEG during this reaction time task. And we found both that there was a very strong effect for the breathing as compared to baseline when they were introduced to this music, We also found that it was very important if we actually personalized the tempo of the way that this music was behaving to their own natural baseline rhythm. So actually, if we introduced music that was breathing at 75% of their normal rate, they actually slowed their breathing down more. We were really interested in knowing this as a design principle, if it makes sense to try to continue personalizing these kinds of biofeedback systems, or if it would be just effective simply to play a CD of relaxing spa music for them. That would be in the case of the orange bar that you see here. So actually personalizing it did affect them more. And we saw similar effects in the galvanic skin response data, also in the ERP that was elicited from this contingent negative variation task that we had given them. So this actually showed that they were focusing more on this task, and in their heart rate as well. So this is just a third example of seeing how we might be able to use musical sounds to affect the body. My PhD student, Mike Winters, recently graduated actually last spring, and he was interested in this case where music performers actually played their heartbeats to the audience. I know that for myself, personally, playing my heartbeat to the audience has often gotten the most feedback from them, where they basically say that it's a very powerful experience. And some people have mentioned empathy as a possible mechanism for that. So Mike was actually wanting to investigate that hypothesis further, to see if hearing other people's heartbeats has an effect on one's own heartbeat, and also on any empathy that is involved in that process. So I'll just play this quick example for you. I want to ask you, if I play this heartbeat of two different people, which of these people would you rather sit down to have coffee with? This is the person on the right, and this is the person on the left. Maybe you can. Oh, Joy can't hear the audio. Did anybody else have trouble hearing the audio? Okay, Annabelle heard it. Hi, Annabelle. Okay, but what you can hear here is, like, on the left, you can hear somebody has a much slower regular heartbeat. On the right, hi Hong. On the right, you can hear that there's a much faster erratic heartbeat here. So what we can see is that we're getting this information, and Garrett says that he likes the person on the left, and that was the answer that I was going for here. So you can see here that you can actually gather a lot of information about this person just by listening to their heartbeat. And you guys are probably gathering that this person, oh, and Mark is asking for a replay. So, okay, I'm gonna play the person on the left here. And then this is the person on the right. And Joy said that they can hear it, but just had to turn up the volume. So these are actually the exact signals that Mike used for his experiments here. These are heartbeats that he synthesized, similar to that breathing work that you saw before. These are kind of synthesized to impart a particular personality. Mark says the right one is him when he opens a grant notification letter. And then Garrett said, the person on the right feels more like me, and I don't want to have coffee with myself. Okay. But we can see how we're getting a lot of personality information, from just listening to this very simple body signal here. Mike wanted to look at what the interaction here was with empathy. So we used this classic empathy measuring task called reading the mind in the eyes. I'm sure that most of you have seen this before. And he was attempting to look at two different kinds of empathy. On the left, we have what is called cognitive empathy, or the ability to basically give a correct name to what somebody else is feeling. So in this task, there was a ground truth here, and that each of these actors was asked to portray a particular feeling, and then we can see how correct our participant was at being able to rate what that actor was feeling here. On the right, we have what's sometimes called affective empathy, what Mike ended up calling emotional convergence, but it's this idea of how much you're able to connect with that person and feel what they are feeling. So these are, two different forms of the phenomenon that we call empathy. So on the left here is really how we're able to put a name to what that person is feeling. Thank you, David. And then on the right here is how we can, how much we kind of open up this information channel and are actually able to feel what that person is feeling. So we gave them this task of seeing these eyes while they were listening to only the audio. While they were seeing the eyes and listening to the audio, we gave them slow, fast beats, and we gave them fast heartbeats as well. So we can see that there's a very complicated experiment design here. But what we found was that the presence of the heartbeats changed the way that the participants rated these actors' eyes. So it had an effect on the cognitive empathy. They also increased the affective empathy when they were in the presence of the visual stimulus as well. So there was no difference between the visual only and the audio only conditions. But then when we introduced that heartbeat sound to somebody viewing those eyes, then we actually found that there was a large increase in this reported feeling that they were feeling what that person was feeling. We also saw here that when the heartbeat speed was congruent with the ground truth emotion of those eyes, we actually found that a mismatch in that congruency very often changed how the person rated the feeling that that eye stimulus was portraying. And in addition, when the heartbeat sound was congruent with the visual stimulus, we had a large increase in the affective empathy rating. There was an effect as well on the participants' heart rate. So when they heard in this audio only stimulus condition, their heart rate was slower during the slow stimuli, and it was faster during the faster stimuli. These two plots, however, are showing that we actually got a more significant result when we looked at only the first half of the trial. So this was kind of a short-lived effect. It only lasted for about 30 seconds, but we did see an effect there. And when we compared people who measured on a personality test of being more empathetic people, we actually showed that they had a larger heart rate shift during this kind of heart rate listening. So the most interesting part about this for me was when we looked at the heartbeat evoked potential in their EEG. So there's actually a ERP that we can look at when we time lock our data around the participants' heartbeats. And this heartbeat evoked potential is thought to index somebody's interoception at that time, which is basically the degree to which they are aware of their own bodily processes. And we found that when we introduced this audiovisual stimulus as compared to the visual only, we saw a drop in the independent component that we attributed to this heartbeat evoked potential, showing that there's a reduced ERP there, in that, possibly that we have less of this interoception happening when you are hearing somebody else's heartbeat. So we can, kind of take this one step further if we're going to interpret this and basically show that when we're listening to somebody else's heartbeat, we are basically putting our own mind into that person's body and kind of experiencing their heartbeat as our own. We are paying less attention, or we are less aware as to what's going on in our own body when we are more aware as to what is going on in somebody else's body. So I'd like to wrap it up here, but I hope you can see how, when we look at all of these projects together, that we're basically trying to elucidate more about how this whole feedback process works. And really what I'm trying to work towards is figuring out not only how we can create these new kinds of music that are going to bring these new experiences to audiences, but also see how we can move towards bringing them well-being as well. And I want to thank all of the people who are on this slide here today.
All right, great. Thank you, Grace. Everybody is silently applauding. I wish we all had EEG monitors so that you could at least see us applauding. But we have a bunch of questions in the chat. It seems like you can see the chat fine, so if you want to just take those, or I can read them out to you as you prefer.
Okay. So maybe I will start with the most recent first, and then we can move back to previous. So Richard Nichols says, thank you, Mark. Sorry, I'm going to be thanking everybody along the way. So Richard says, to what extent are other autonomic variables affected in association with effects on heart rate, such as cortisol secretion? That is a very good question. I don't work with the technology that allows me to monitor cortisol secretion in real time. I'm really interested in technology where I can monitor in real time and then convert that into feedback right away. Because I started out as a EEG person and then kind of moved towards the physiology after that. But I can tell you that there's been, several lab studies that have showed that things like cortisol secretion, dopamine as well, can be tracked, and showing that there's a tight link between neurotransmitter release and these kinds of spikes in autonomic activity that we see during peak musical experiences. I guess that's the most that I could answer that question in the container allotment that we have right now. I'll answer Eric. So how would you expect the closed loop feedback for music to change if we had different recording methods for human neurophysiology? So better resolution or access to more localized brain signals. That's a very, very good question. I think that, when you're bringing up this closed loop versus open loop effect, there's a very strong effect of training in this. So we have to understand that when a performer goes on stage, just like if you saw Sophie Mutter go on stage and perform the violin. Well, this is a very complicated physical system that she's had decades and decades to perfect through this kind of, closed loop system, what these very strong changes are that she's going to make, or sorry, very subtle changes that she's going to make with her finger position and bowing to create this sound. And in a very similar way, there's a process going on in there when somebody learning brain music performance develops this kind of simple algorithm, but then most of that expressive potential comes in this kind of operant conditioning of how the human is learning how to make these changes in their EEG to produce a particular sonic difference in the sound, so you can create this kind of expressive arc over time. And so when we have more resolution, I wouldn't necessarily mean that, say that would mean that we would have a better performance coming out of that. It would probably take more time for the person to try to figure out through that process of experimentation how to develop ways to control that. But one type of experiment that I would love to work on with somebody here at Georgia Tech would be to take a group of people and to develop a fMRI biofeedback system using, one tiny mechanism there, and to see if they can learn through this process to control their feedback, just by having that biofeedback present in the scanner. So I will end Eric's answer there. Let's see. I'm just reading back to some earlier questions. Oh, I don't think that we have any that I didn't answer yet.
There was a couple of questions at the end now.
Yeah, let's see. So Annabelle mentioned that there's really interesting research examining how well people can detect their own heartbeat. So yeah, this is getting back to this interoception idea of how aware are we of our autonomic nervous system operating as it's operating. And Annabelle mentions that there's deficits in this ability in disorders like autism. So yes, actually, in autism, we have a deficit of this theory of mind, right? But we also have a deficit of this own personal interoception as well. And so that's very interesting that you would see that link between those two deficits, but also in the result that we have here that, when we're kind of witnessing this interoceptive process happening and the attention being transferred away from that, that we're seeing the process of interoception being interrupted here. So Joy says, have I ever thought about trying to produce brain music with a choir or a group of performances versus just an individual? So I have done some performances in small groups, but there, I also need to mention that I'm not the only person doing this work, and there is some colleagues of mine, for instance, who created the company that creates the Muse headsets, Interaxon. They actually gave a performance where they handed out dozens of these to people in the opening ceremony for the I guess there was Olympics in Toronto not too long ago. So that was a very early brain performance that was actually looking at, you can run some interesting calculations looking at correlation in between, people's brain waves. So there has been some work with that before. But I've really been focusing on this kind of solo work. So Hong is asking, during EEG and other signal recording, anything else you try to remove motion artifacts except trying to be steady? Yes, so Simon mentioned that I did my PhD at the Swartz Center for Computational Neuroscience. They maintain EEG lab, and they also have some real-time software that they've developed called BCI Lab. And there's an algorithm in there called artifact subspace recognition, which runs like a sliding window PCA on the signal, and you can actually extract motion artifacts from EEG that way. So I don't use this software for every performance that I run, but if I'm willing to have 3 or more computers that I'm working with on stage at the same time, that usually takes an entire laptop just for itself. But I have done that before. Um, so there are definitely methods that we can use. Of course, they work a lot better in non-real time. Um, so the limitation is what we can do on the stage. Um, So Sherman asked, can seizures be induced by specific music tones? I would say that, there's a lot of literature showing there's actually musicogenic epilepsy. So there's some people, when they listen to a Mozart piano concerto, have seizures as well. So epilepsy tends to be a very individualized pathology in terms of what presents for every individual, and music and sound can play a part in that.
Great. All
I
right.
have
I want
addressed all the
to thank.
questions.
Yeah, these were excellent questions. Made my job really easy because they were all up there. Thank you all. But I think we need to wrap it up now so that people can get on to the next thing. I know Grace is trying to get moving as well. So let me thank Dr. Leslie again. Everybody is applauding. You can see everybody's mental waves, right?
Thank you,
Brain
everybody.
waves.
This was really fun.
Celebrating.
Um,
I think this really celebrates the diversity of neuroscience and its various applications that we have on campus. And so I really enjoyed this. Thank you so much. That was great. Join
and
us
I'm
next week
typing
again, please.
I just typed my email address in the chat window as well. So I would love to hear from everybody about your thoughts and about, collaboration opportunities.
Thank you. Thanks,
Thank you,
everyone.
Simon. Thank you, everyone.